Okay, so again, when you combine big phi, the azimuthal functions, big theta, the polar functions, into y, and now we know that these are quantized. So they just to remind us that there's only particular values of L and M which are allowed. Then we can write the YLMs, which are known as the so-called spherical harmonics. These are used in things like electrical engineering to analyze things like filters. Okay, and so the first few are written here. So y00. Remember, m sub l can only go from minus l to plus l, and so if l is equal to 0, then m has to be equal to 0. And so we basically just are left with the normalization constant square root of 1 over 4 pi. If L is equal to 1, but ML is equal to 0, we get root 3 over 4 pi times cosine theta. If L is equal to 1 and M sub L is equal to plus or minus 1, we get minus or plus. That is, the minus goes with ML is equal to plus 1. The plus goes with the ML is equal to minus 1. Root 3 over 8 pi times sine theta e to the plus or minus I to the phi. Again, plus now goes with minus, goes with plus, minus goes with plus, goes with minus. Okay, and so on. Okay, you can look at these yourself. You can look at these. It's a little bit hard to make sense of these just from looking at them. So we're gonna, in the next view graph, I'll show you. In the next couple of view graphs, I'll sort of show you what they look like. Okay. And this set of functions are known as the spherical harmonics, and as the solutions to the 1D harmonic oscillator or the 1D infinite potential well, those eigenfunctions, the solutions were a complete orthonormal set. The spherical harmonics are also a complete orthonormal set, which means that if you integrate YLM star, that is the complex conjugate of YLM, times YL prime M prime, so these are two different values of L prime and M prime. Okay, you integrate those from phi from 0 to 2 pi, theta from 0 to pi, sine theta, d theta, d phi. What you get is a product of two Kronecker delta functions, which means that L prime has to equal to L and M prime equals to M, and otherwise this is 0. And if L prime is equal to L, M prime is equal to M, we're back to the normalization condition up here, and that's equal to 1. All right. So it's a complete orthonormal basis. So you can write any function, any superposition state, as you can write any arbitrary function of theta and phi that satisfies the same sort of boundary conditions. That essentially means continuity. As a superposition of this basis, of these basis functions. Okay, so here are the polar solutions. These are the phi sub L, phi sub L's, phi L MLs, and here this is from your book. Again, this is from Harris. Okay, and it's these are now have been squared. Okay, so we're looking sort of at the probability density when you look in the different directions. So the way that you interpret these is that you imagine we have a vector, okay, which goes off in some direction, and in some direction theta. Okay, so then theta is the polar angle. Okay, so we're this line here is meant to represent the xy plane looking from the side, and this is the z-axis. And you look off in some direction theta, and the shape of this tells you what the relative probability density is. Okay, so for L equals 0, ML equals 0, we see that in every direction we're equally likely. The probability density is the same. Okay, so we're equally, in some sense, if you only consider we haven't considered the radial part of the wave wave function, but if you only consider the polar part, then if you look off in any direction, any value of theta here, you're equally likely to find a particle in a central force potential, so an electron and an atom, for example.